In mathematics, an algebraic surface is an algebraic variety of dimension 2. In the case of geometry over the field of complex numbers, an algebraic surface has complex dimension 2 and so of dimension 4 as a smooth manifold. The theory of algebraic surfaces is much more complicated than that of algebraic curves dimension 2. Many results were obtained, however, in the Italian school of algebraic geometry, and are up to 100 years old. Classification by the code error dimension. In the case of dimension 1, varieties are classified by only the topological genus, but dimension 2, the difference between the arithmetic genus and the geometric genus turns to be important because we cannot distinguish birationally only the topological genus. Then we introduce the irregularity for the classification of them. Let's summarize the results. Examples of algebraic surfaces include kappa equals minus infinity, the projective plane, quadrics in P3, cubic surfaces, Veronese surface, del Pezzo surfaces, ruled surfaces, kappa equals 0, K3 surfaces, abelian surfaces, Enrique's surfaces, hyperelliptic surfaces, kappa equals 1, elliptic surfaces, kappa equals 2, surfaces of general type. For more examples, see the list of algebraic surfaces. The first 5 examples are in fact birationally equivalent. That is, for example, a cubic surface has a function field isomorphic to that of the projective plane, being the rational functions in two indeterminates. The Cartesian product of two curves also provides examples. Birational geometry of surfaces. The birational geometry of algebraic surfaces is rich because of blowing up, under which a point is replaced by the curve of all limiting tangent directions coming into it. Certain curves may also be blown down, but there is a restriction. Properties. The Nakai criterion says that a divisor D on a surface S is ample if and only if D2 greater than 0 and for all irreducible curve C on SDC greater than 0. Ample divisors have a nice property such as it is the pullback of some hyperplane bundle of projective space, whose properties are very well known. Let be the abelian group consisting of all the divisors on S. Then due to the intersection theorem is viewed as a quadratic form. Let then becomes to be a numerical equivalent class group of S and also becomes to be a quadratic form on, whereas the image of a divisor D on S. For an ample bundle H on S, the definition leads the Hodge index theorem of the surface version 4, i.e., is a negative definite quadratic form. This theorem is proved by using the Nakai criterion and the Riemann-Roch theorem for surfaces. For all the divisor in this theorem is true. This theorem is not only the tool for the research of surfaces but also used for the proof of the Weyl conjecture by Deligne because it is true on the algebraically closed field. Basic results on algebraic surfaces include the Hodge index theorem, and the division into 5 groups of birational equivalence classes called the classification of algebraic surfaces. The general type class, of code error dimension 2, is very large. There are essential 3 Hodge number invariants of a surface. If those, H1, 0 was classically called the irregularity and denoted by Q, and H2, 0 was called the geometric genus PG. The third, H1, 1, is not a birational invariant, because blowing up can add whole curves, with classes in H1, 1. It is known that Hodge cycles are algebraic, and that algebraic equivalence coincides with homological equivalence. So that H1, 1 is an upper bound for ρ, the rank of the any-acute RON Severi group. The arithmetic genus bar is the difference geometric genus minus irregularity. In fact, this explains why the irregularity got its name, as a kind of error term. Riemann-Roch theorem for surfaces. The Riemann-Roch theorem for surfaces was first formulated by Max Noether. The families of curves on surfaces can be classified, in a sense, and give rise to much of their interesting geometry.